Hi, in this video we want to take a look at overdispersion in Poisson regression models. All right, so this is an example that's modified from generalized linear models with examples in R. So there's the book, there's the authors, and there's where you can get it on Amazon. You can also download it through Springer Link. All right, so if you think about the Poisson distribution, one major feature of it is that the mean and the variance are equal to each other for any Poisson distribution. So if I'm using Poisson regression, I want to see that my modeled expected value and the conditional variance are going to be close to each other. Okay. All right. So what if it's not? Well, if the variance is greater than the mean, then we have overdispersion. And if the variance is less than the mean, we have underdispersion. Now, for Poisson regression, we want to be about equal to each other. We don't want over or under, but in practice, overdispersion is more common to see, and it's more of a problem, really. All right, so overdispersion usually arises when there's like some innate variability that hasn't been taken care of with the predictor variables, or the events are being counted are correlated with each other. So we don't have uncorrelated observations, like one of the important assumptions in regular regression. All right, so overdispersion typically arises because the events being counted arise in clusters or are mutually supporting in some way. This causes underlying events to be positively correlated, and overdispersion of the counts is the result. And this part is actually copy and pasted from that book, by the way. All right, so we've got two major ways for detecting overdispersion. So first one is to look at the residual deviance. If it's larger than the degrees of freedom, that's a problem. If the Pearson goodness of fit is larger than the residual degrees of freedom, that's a problem. That's an indication of that we have overdispersion. Now, when I say greater, it has to be like substantially greater, not like a little hair tiny bit more, like, you know, something like real. Something like, yep, that's bigger for sure. All right, so when we see it, something that we can do, we can try like throwing in some more predictor variables, and we can go through and remove problematic data points. If that doesn't fix the overdispersion aspect, then we're going to need to do something else. Now, if I'm looking at it and I see that I've got lack of fit statistic is coming up as being, you know, big, something significant. So I've got, you know, say something signaling lack of fit. So it's either lack of fit or it's overdispersion. It's one or the other, maybe both. If you don't know, conclude that it is a lack of fit. That's a safer way to go. All right, so what we're going to do, we're going to use the POC data set from the GLM data package, and then we're going to, you know, start working through this example. All right, so I load the data from the package, and now something I did, I went ahead and I sorted the data by dilution, then by count on this line. Now, why did I do that? Well, when I look at the data in this format, I can see that the largest predictor variable values are appearing with the smallest count values. And if I go at the other end, I can see that the smallest predictor variable values are going with the largest target variable values. So I can see that just at a glance, I probably have a negative correlation. So this column is sorted from largest to smallest, and this one, it's not quite sorted, but it is looking pretty close to it. So I'm feeling like there's probably something going on. There's probably a relationship between dilution and the number of POCs. All right, now something I did, I changed the row names to go from 1 to the number of rows. Why did I do that? So that way when I do my diagnostic plots, it's easier to infer, am I looking at, you know, extreme values? If I see like, you know, number 3 in the diagnostic plot comes up a lot, well, that's one of the, you know, lesser counts, larger dilution values that might help me spot something. All right, now on the next step, I'm going to go ahead and define colors. So I thought about dilution. To me, high dilution is probably like blue. Like I'm mixing it up with water probably. And low dilution, I just picked as red. And so I went ahead and used color ramp to create a color palette function. That's it. So this creates a function for generating colors. And what I do, I just have to pass the number of colors I want. And then I'm going to color by the dilution because I only have 5 distinct values. All right, so let's go ahead and do that. Now, the author is working with the log of the dilution instead base 2. And if I look at the original data, that makes sense. I see that everything is a power of 2. Remember, anything to the power of 0 is 1. All these 1s correspond to 2 to the power of 0. 16 is 2 to the power of 4. All of these are powers of 2. So it makes sense that for my modeling, it seems reasonable that I will be working with log base 2 of the dilution. And the author chose to go log base 2 of count also, which is fine. I would have left it as is, but either way, it's all good. All right, and so we can go ahead and take a look at this. And so we can see that there's a so when I look at box plots, if the boxes look like this, I lean towards central tendency being equal to each other. If it looks like this, if the boxes look like that, then I'm leaning towards central tendency being distinctly different. So if I look here, central tendency is different here, a little bit of overlap, but the median lines are not slicing each other's boxes. So I feel like there's probably a difference. I feel like there's probably a difference each step of the way. So at this point, I conclude that dilution has good informative value towards count. All right, so now I want to use Poisson regression. Why do I want to do this? Well, it's count data. And generally speaking, I want to try to use a modeling system that relates to my target variable. POCs are counted in counts. Therefore, I want to try Poisson regression. I might use Gaussian just to see what's going on. It might be that the Gaussian assumptions fail also. Okay, so let's take a look. So what I'm going to do, I'm going to go ahead, I'm going to find the average target variable value by each of the predictor variable values. So what I'm doing here, for each distinct value of dilution, I'm taking the average of the counts. And here I'm using mean is the function. Now down here, I'm doing the same thing. I'm taking each of the counts, I'm grouping them by the predictor variable value, but then I take the variance. Okay, and so now what I'm going to do after I get that, I'm going to go through and I'm just going to plot it as a scatter plot. Let's see what happens. If I have a good solid framework for doing Poisson regression, the mean and the variance will be approximately equal to each other. All right, so let's take a look. All right, so here we've got the mean, and here I've got the variance going. All right, so this is the average POCs count for the high dilution amount. So remember the coloring scheme I had previously, the bluest was highest dilution, the red was lowest dilution. So here we know that this is high dilution, low dilution, and then these are in between. Okay, so this X value is less than 4, the Y value is slightly greater than 4, so it has greater variance. Here we can see that the X value of this point is a little bit less than 5, the Y value is greater than 7. We have greater variance in this group than we do mean. I come over here, this is less than 6 in the X coordinate, Y coordinate, it's greater than 8. We have greater variance. And I keep on going down the line and I can see that on every single dilution level, we have greater variance than we do sample average. Okay, and you'll notice I put the AB line of A equals 0, B equals 1, so y-intercept of 0 and slope of 1 right here. This is showing me that at a quick glance that every single time the variance is greater than the mean for each of these groups. Okay, so I conclude that I have overdispersion. All right, so let's go ahead and make a data frame to kind of visualize this. So here is the mean of the counts, variance of the counts, and then this is the variance divided by the mean. And I can see every single time the variance is going to be bigger because every time the ratio is greater than 1. And we can see that the ratio is the least for the largest dilution, and it's the greatest for the least dilution. So this is something very interesting about it. All right, now if I go through and I do a linear model trying to fit the log variance by log mean without an intercept, I can see that we get a slope of 1.5. If you work through the college algebra of what I've been working through with this type of modeling, we can see that this corresponds to a variance function of about 1.5 exponent on the expected value. So we do not have equality between our variance and our expected value. All right, well, let's go ahead and let's build the Poisson regression model. All right, what I'm going to do, I'm going to build a Poisson regression model, and I'm going to use each of the 3 links. Why? Because I'm trying to find a good fitting model. I want a model that works very well. Now, in a lot of scientific work, a lot of pure statistician work, you would say that you would have a theoretical belief about what's going on, and you use subject matter knowledge to tell you what the link function should be. A lot of times, honestly, if you're publishing papers, it's just what other scientists just chose to do, and you just do what they did because they did it before you. That is the real deal of what happens. It's very frustrating when you get into the situation that you build a better model, but they reject it because they're not familiar with that link function. It happened to me. I'm bitter. But okay, so what I'm going to do, I'm going to use the GLM function to build my generalized linear model. Each time I'm going to use count depends on log of dilution. I'm using the Pox data set, and family will be Poisson every single time. For this set of code, what's changing is that I am changing the link. The link is either going to be log, square root, or identity. And I'm going to store everything in a list. And why do I store it in a list? Because that keeps everything all nice and neat for me. All right, so now at this point, I have 3 models. And I want to get a feel for model quality. I want to get a feel for overdispersion. Do I have it? Overdispersion, underdispersion, have we hit that sweet spot? So what I'm going to do, I'm going to get the degrees of freedom on the residuals, degrees of freedom, or excuse me, the deviance, and I'm going to get the Poisson goodness of fit. Now you'll notice what I'm doing, I'm using the sapply function. What I'm telling R to do, sapply says, apply this function to every single item here. So for every single model in this list, I'm going to apply this function, and the output is going to be this column of my new data frame. All right, so I'm going to take every model in this function. I'm going to apply this, every model in this list. I'm going to apply that function to every single model. And then the output is going to be the deviance of this data frame. And then I do the same with the Poisson goodness of fit. You'll notice it's just the sum of squared residuals. All right, so now I look at this. So I've got degrees of freedom of the residuals, the deviance, and the Poisson goodness of fit. Well, when I look at this, I can see that these are substantially bigger than the degrees of freedom. I conclude that I have either a lack of fit or overdispersion. Either way, at this point, I'm not feeling the love for the regular Poisson regression. All right, so let's try something else. What I'm going to do, I'm going to try negative binomial. Negative binomial has count data, so it's a reasonable thing to go with. And I'm going to go through, I'm going to do the same thing. I'm going to be changing up the link. But the difference here is that for negative binomial, that's not available in the default normal stats package GLM function. What I have to do, I have to go into the mass package and I get glm.nb. NB is for negative binomial. And so the syntax is a little bit different. So when I get the output from this function is not going to be the same format as a generalized linear model like I did a moment ago. What I need to do, I need to convert it to be the same format. That way, as I proceed and I work through everything, I have everything as organized and the same as possible. It's the same formula, same data set. The links are, you'll notice that these are different. I'm not stating the link inside a family function. I'm stating the link inside the glm.nb function instead. And then I go through and I do the same thing. All right, so now when I grab the degrees of freedom of the residuals, the deviance, and the Pearson goodness of fit, I see that things are pretty tight. Okay, so I conclude that for these three negative binomial generalized linear models, I conclude that I do not have an overdispersion problem. So this makes me feel good. I'm feeling the love on this. Now, another option is to go with quasi-Poisson regression. And so algebraically, this is a more complicated version of Poisson regression. That's really, at this point, the main takeaway for it. The only difference between this and the GLM models that were built a moment ago is that I'm putting the term quasi in front of Poisson. Everything else is the same as the GLM models previously produced. And then after that, I go through and I get the statistics, and I can see that this is very similar to the regular generalized linear model Poisson regression. Okay, so now what I want to do at this point, I have 9 different models. I want to pick the best one. Now with negative binomial, I'm seeing that I don't have an overdispersion problem. So what I'm going to do, I'm going to go ahead and change up the names in the list so that it includes the family of the generalized linear model. And then I'm going to put them all together into one list. That way I can work with all 9 models at the same time, make my life easier. And then I'm going to evaluate the dispersion like I did before. And I'm going to evaluate the mean absolute error. All right, so mean absolute error, what I'm doing, I'm taking observation, I'm taking residual, subtract absolute value, and then take the average of all of those for each model. So the mean absolute error it's similar to the mean squared error, but instead of taking a square, I take the absolute value. I feel that this is a better metric for model quality, and it's a better metric for communication. All right, so if I tell you the MSE is, let's say, 300, is that big? Is that small? I don't know. I can't reference it off of anything because I squared it, added up, took a square root. It's very different. Now, if I look here, look at these values. These are going from 15 to 23-ish. 15 to 23. If I go back up here and I look at this, 15 to 23, that's inside this range of my observations. All right, so this gives me more an intuitive feel of how does my model perform compared to the original target variable. And so if I'm off by 15, I mean, that's a good amount. But if I'm talking about the situation where it's 260 pox, 15 off, I mean, yeah, that's kind of high, but that's not horribly high. Honestly, I would say 15 is bigger than we really want to be. There's what? It's like about 30% off from the median. So that's not inconsequential, but it's easier to interpret. It's easier to communicate to somebody who's not familiar with squaring everything, adding it all up, and then taking the square root in the mean squared error. All right, so let's go ahead and look at the bar plots. And unfortunately, this got clipped, and I was trying to fix it I didn't feel like it was worth it, so I just went ahead and launched anyway. But we can see that I got log, 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 square root, square root, square root, identity, identity, identity. For this data set, we can see that really the link function is more important than the family of the generalized linear model. Huh, okay. So then, among the logs, I can see I've got Poisson log, quasi-Poisson, and then I've got negative binomial. All right, and we can see that, you know, these two are the same, quasi and non-quasi. Well, which one would you go with? Well, Poisson regression is a simpler model, so I would lean towards this one between these two. Between these two, I would go with the simpler one because I'm getting the same statistic out of it. Now, if I want to take a look at dispersion, over dispersion, then when I look at this, I can see that negative binomial is my best performer. I have this ordered by the mean absolute error. And I could do a little bit better with the square root and negative binomial. I can do even better with negative binomial and identity. Personally, what I would do in real life, if my goal is to get the best prediction possible or best model possible, I would go with Poisson regression with the log link function, which is the default link. Now, if I'm in a situation where the people I'm working with or the people who are going to be reviewing my work just absolutely hate over dispersion, then I would go with negative binomial with the log link function. That's how I would proceed. Remember, when you build a model, you need to always consider like who your audience is, what is its purpose. A weaker model that is accepted and used is superior to the best model on the possible that never gets touched. All right, so now let's go ahead and take a look at the coefficients. Now you'll notice that if I look at all of the log link function models, the coefficients are pretty close to each other. If I look at the square root link functions, the coefficients are pretty close. And if I look at the identity, I can see link function, I can see that the coefficients are pretty close to each other. All right, why is this? Well, remember, the link function really is the bridge between your data and the equation that you are using for to fit the model. All right, so the family, Poisson, quasi-Poisson, negative binomial, that is how it's actually fitted. But the link is how you connect between the two. And here we can see that that link is very important. That really the link is like the driving aspect on this data set. All right, so in real life, if I was to truly launch this model without having to worry about over dispersion, I would use Poisson regression with the log link function. Why? Because I get the best mean absolute error. And so here is the model. Here's the AIC. And I can look at the summary of it. I can see that the coefficients are statistically significant. I can't interpret the AIC, unfortunately. And now I'm going to go ahead and plot to see if there's anything jumping out at me, just as a check to make sure that this is a good model to launch. Maybe I want to remove some observations possibly. Now, when I look at these plots, remember, R is always going to label the 3 most extreme values. The 3 most extreme values will always be labeled. So just because it's labeled doesn't mean I need to throw it out. Just keep that in mind when you look at your own plots. So look here. All right, I see the line looks pretty flat. Residuals are going from -6 to 6. That is rather large, but yeah, all right. Normal plot. This looks like a little bit higher up than I would like, but this one comes back down. You know, it's never absolutely perfect, so I'm not going to sweat this part, but I accept it for what we're doing. Square root of the standard deviation of the residuals. Yeah, this is, I'm not seeing any issues with this. You know, I see that flat line. Here's my Cook's distance. Now, something that jumps out at me is that here, Well, notice that all of the large cook distance correspond to low dilution, and low dilution was higher counts. So I feel like this corresponds to that overdispersion aspect. Remember, this model does have overdispersion. I think that this end of the data is probably contributing to that. And residuals versus leverage, we can see once again the low dilution is at the far end, far off from everybody else. And then cook distance versus leverage, same thing. Low dilution is popping up again. So this is a really good example of why I always color my points by an important variable, because I can spot that that's going on with, you know, it looks like the low dilution observations are not consistent with the rest of the data for Poisson regression. I still feel like this is the best of the 9 models, but if another model structure came up, I would definitely give it a shot. Well, thank you and goodbye.